Welcome to our lecture on vector functions. This one should be pretty easy because most of what you wish would be true turns out to be true. But let's talk about why that is. So first, let's give a definition. A vector-valued function is a function whose domain is a set of scalars and whose range is a set of vectors. So this notation here, the bold-faced R, it maps, it inputs R and outputs things in R2 or R3. So that means what we're talking about in this chapter is we have a single number, real number we're plugging in, and we get a scalar, either 2 components or 3 components back out. I like to think of the t, the input, as time. And so we can write these in the component form. We can write f of t, g of t, h of t, or fti, gtj, hth if you prefer. These two forms are just as good as each other. So what happens is each of these 3 parts are scalar functions. Each of these is a regular one variable in, one variable out function, just like you would have in regular calculus. And so they provide your x, y, and z. Now, I like to think of these as latitude, longitude, and altitude of a rocket. You shoot a rocket into space, you watch it go around, and you have 3 different gauges measuring each of the 3 component functions, each of the 3 coordinates it can have. If we're on the ground, you would just be latitude and longitude. All right, so the domain. So someone asked me the other day, domain is x, range is y, what is z? And that's not really the way to think about it. What you want to think about is in terms of input and output. So in this case, the inputs are t's. The outputs are vectors that are in x, y, and z. So x, y, z collectively can be the output. So domain. So we can say the domain is just the intersection of the domains of the component functions. The idea there being, if one of the 3 parts is undefined, then the whole thing's undefined. You have to have all 3 of them defined. So let's find the domain of this function, t cubed, natural log of 3 minus t, square root of t. All right. I'll clear this off. So the domain for the x component, well, the x component was t cubed. So t cubed is defined everywhere. So domain is negative infinity to infinity. Domain of the y component. Well, now, the y component was ln of 3 minus t. Now, natural log is only defined for positive numbers. So we can say 3 minus t needs to be greater than 0. And again, if you take anything with complex imaginary numbers, you can break some of these rules, but we're just going to stick with real numbers in this class. So this, we can add the t over to the other side. 3 is greater than t. Or if you want to flip it around, t is less than 3. Just the arrow is pointing at the t here, the arrow is pointing at the t here, so this means the same thing. So the domain is t is less than 3, so negative infinity to 3. And for z, well, the function was square root of t. So the domain of z, we need the t to be greater than or equal to 0. So it's 0 to infinity. And include the 0 because square root of 0 is just 0. So then the domain of the big function r is just whatever's in all 3 of these. So dx is everything. dy is everything up to 3. dz is everything greater than or equal to 0. So the actual domain here would be 0 to 3. That is the interval on which all 3 components exist. And if you go outside of that interval, either the y or the z are going to be non-existent, and so therefore that's not in the domain. So hopefully that's pretty easy. Now, calculus is based on limits. It wasn't always, but in today's calculus, that's how things are done. So we want to come up with a definition of what a limit is. Because if we can get limit to work, then all the things that come from it, derivatives, integrals, series and sequences, everything can just be carried right over. So what we hope is that we could just do the limit of each component separately. Our vector function has 3 regular functions inside it. So can we just distribute this limit in one by one? And that almost seems too good to be true. So we need to do a little something to justify whether or not we can do this. And so we're going to take a bit of a step back into what's called topology, which is the study of closeness. Because this is, if you go on to more advanced studies, and this comes up in like vector arrays, you computer people, you might have, say, an array with 10,000 different entries in it. Well, that's like a 10,000 dimension vector. So what does it mean for two 10,000 dimension vectors to be close to each other? Now, we're not going to get that big in this class, but I want to give you an idea of how we reason through these things, because there's more than one answer. But I want to come up with the one that makes the most sense for us. So, we're saying limit as t goes to a of r of t equals L. So what that means is that if t, the time, is close to some specific time a, then the vector we get when we plug in t should get close to some specific vector L. So let's draw a picture for that. So let's say the L vector is right here. And I'm using the arrow because L is a vector. Remember, the input t is a scalar, but the outputs are all vectors. In this case, I'm going to draw it in R2. Well, we'll imagine it's in R3. So the idea is, we can say, if R of, let's say, we plug in A minus 1. We get a vector over here. Then we plug in A minus a half. We get a vector a little closer. We plug in A minus a quarter. We get a little closer. And maybe it's not only minus, maybe it's also plus. We plug in R of, let's say, A plus 1/10. We get closer. So you see the inputs are getting closer and closer to A. And we see the vectors are getting close to L. But again, what does it really mean for two vectors to be close? Well, we're going to say all the vectors are based at origin, because they're all equivalent, so we might as well give them all the same base. So then, the only thing that's different is tips should get close. In fact, what we can do is we can say, well, let's draw a circle around the L, draw a ball around the L, and we will say the outputs, these vectors we get, will end up inside the ball. And we can even say the radius of the ball is epsilon. So we're saying two vectors, u and v, are close when tips are close. Well, how far apart are the tips of these vectors? Well, we said a while ago, if we want to measure the distance between the tips, that is the same as subtracting the vectors. So distance from tip to tip needs to be small. So distance from tip to tip is the length of u minus v. That was just something we said early on. The distance between the tips of two vectors is the same as subtracting them. So, I shouldn't have put the absolute values there yet. Well, the length of u minus v, which is absolute value of u minus v. So this is very valuable. Vector algebra, linear algebra and whatnot, is an extremely versatile field because it applies to so many different settings. And so anytime you're dealing with vectors, this is how the distance is defined. You take the two vectors, you subtract them, and then you say, how long is the vector you get? And then that depends on how you measure length. There's more than one way to do that. But so what we mean is, but we have our way of measuring length, which, let's just spell it out here, would be the square root of u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared. Sometimes people who've been doing math for a long time start going off on unrelated subjects or things that are way too advanced for the class. So when I start talking about different ways of measuring distance, I really probably shouldn't do that, because in our class, this is how we measure distance with the Pythagorean theorem. So we're saying this needs to be small when t minus a is small. We let t get close to a specific time, and the distance between two vectors should also get small. So let's be a little more formal about this. We won't normally go to this level of formalism, but I want to spell it out the first time just to give an idea of what's going on. So let's look at the epsilon delta definition. So we're saying we want to define limit as t goes to a of r of t equals vector L. What does that mean? Well, it means, if we go back to definition, given some epsilon greater than 0, there exists, that does not look like an arrow, let me fix that, a delta greater than 0 such that if t minus a is less than delta, then the distance from vector r of t minus vector L is less than epsilon. And we said that is the same as saying that if you draw a ball around L with radius epsilon, then the r will be inside that ball, the tip of it will. Well, let's expand what this means. Okay, so what does r of t minus L less than epsilon mean? Well, r of t minus L is, no, we used f, g, and h, didn't we? F of t minus Lx, g of t minus Ly, h of t minus Lz. We have those three different components. We're saying Lx, Ly, and Lz are the three parts of L, so we just subtract component-wise. Well, what's the length of this? Well, we will do the square root of f of t minus Lx squared plus g of t minus ly squared plus h of t minus lz squared. So that's the distance. And now I'm not going to go through every single step of the thing, because what I want to say is this is less than epsilon. When is this less than epsilon? Well, it's less than epsilon if and only if ft minus lx is small and gt minus ly small and ht minus lz small. Each of these are squared, so each one's positive. So each one of them would have to be close to 0. And so, well, that means if each one of these are small, that means the limit as t goes to a of f of t equals lx. And the same is true for the other ones. Limit as t goes to a of g of t is ly. And limit as t goes to a of h of t is lz. But that means this is exactly what we want in the first place. That instead of trying to do the whole limit as one big piece at a time, all at once, we can split into do the f limit, the g limit, and the h limit all separately. So that's good. That's very good news for us. And like I said, if you were in some other setting, you might have to do this same process to try to show that you're allowed to split it up this way. But we've just shown that, yeah, you can. So, that's some good news then. We are saying that when we're asked to do a limit like this, we can just do each limit separately. So let's do this example. Find limit as t goes to 0 of r of t, where r of t is 1 plus t cubed I plus t e to the negative t j plus sine t over t k. Well, this would equal then each individual limit. Limit as t to 0 of 1 plus t cubed. Limit as t to 0 of t e to the negative t. And limit as t to 0 of sine t over t. Okay, so let's go through it. First one is 1, because you just plug in 0 for t. Second one, you just plug in 0 for t. You get 0 times e to the 0 is 1, so 0 times 1 is 0. Third one, sine of 0 over 0, undefined. As t approaches 0, it actually comes out to 1. That is one of the limits you're supposed to memorize in Calculus 1. Now, I guess you can use L'Hopital's rule to do it. That's kind of a cheat because to use L'Hopital's rule, you have to already know the derivative of sine is cosine. But the only way you could know that is if you'd already done this limit. Regardless, the answer is 1. And so, yeah, this is just sort of a fundamental trig limit. Sine t over t. If you take t to 0, you get 1. So the answer is 1, 0, 1. Or if you prefer, I plus k. Again, these two forms are identical, so use whichever one you prefer. It does not matter to me. All right, so let's go on to the next one. Let's talk about continuity. What is continuity? Well, we learned this back in Calc 1 in concept. it needs to have the limit has to exist, and you also have to be able to plug in directly, so not just take t to a, but also plug in a to r directly, and they should give you the same thing. Well, since continuity is based on limits, we can say r is continuous if and only if all of its component functions are continuous. And again, graphically, this means the vector changes smoothly as we change t. It's not going to suddenly jump from one side of the page to the other. If we look at this other one, this one we just did, these functions are each continuous. This one, sine t over t, is not continuous at 0, because if you plug in 0 directly, it doesn't exist. So we would say the function overall is continuous ever except t equals 0. Okay. The good news with continuity is most functions that you can name and give an easy description of, they're going to be continuous everywhere except where they're undefined. So, for instance, sine t over t, it exists everywhere except 0, so that means it's also continuous everywhere except 0. The main exception we deal with is piecewise functions. Piecewise functions, since they are by design to have a break in them, so we have to be careful that whether it's continuous there. All right, so let's talk about what a space curve is. And it is the set of points x, y, z, where the vector x, y, z is f of t, g of t, h of t. So that basically means we use the t to get vectors, and we change those vectors into points, and then we graph them as t varies over some interval I. So I'm going to do a couple common examples here. What is this curve? Well, if you remember what we did last week, this is a line. This is a directed line along the vector 1, 5, 6. So I say directed line because we are always going to assume t is increasing. So we have this line here. Goes in both directions. Well, we should probably not have arrows on both directions, actually. We should probably have arrows in the positive direction. So let's take off that back one. Let's say this vector here is 1, 5, 6. And so this is the space curve created by it, where here's, let's say, t equals 0, here's t equals 1, up here would be t equals 2, back here would be t equals -1. But yeah, when we're dealing with these curves, you always want to indicate which direction it's moving. So you can put an arrow, put a bunch of arrows if you like. You like to fill it in, it's up to you. So yeah, it's just a line. All right, let's see the next one. Sketch curve whose vector equation is cosine of ti, sine tj, and tk. This example shows up a lot, or variations on it. So let's study this one here. What do we get here? We have r of t is cosine of ti plus sine tj plus tk. Oh, someone's emailing me, it sounds like. I'll deal with that later. Okay, so in x and y, when x and y is cosine and sine, that is a circle, radius 1 in the counterclockwise direction. So the 2D curve looks like this. And if it were just x and y, that would be the whole thing. It would just keep looping around on itself forever. But we also have z equals t. So that means it'll be increasing. So what we get then is our coil. Here's X, Y, Z. And so we will say, like, here is the circle that we will be following. But in fact, we'll be going up as we go. So it'll look like this. My drawing is not perfect, but ideally this would be, each one be exactly above the one below it. So if you were watching from above, you would just see it going along this circle over and over again. But if you're watching from the side, you can see it's actually going upward as time goes by. And if you could go back in time, it would even go down below. Still pointed upwards. And of course, you could do this in the graph, in the 3D graphing, and see it. Let's see. In fact, I encourage you with these to pull up the graphing software, plot it, and see what you get. Okay, what's next? All right. Find a vector equation for a line segment that joins these 2 points. Okay, we have done this before, but as a line segment. So, this is kind of review. It's a vector function, but it's not anything we haven't done before. But, well, R of t. Remember the formula, the shortcut formula was R naught times 1 minus t plus R1 times t. Well, here R naught would be the starting point, 1, 3, negative 2, 1 minus t, plus R1, the ending point, 2, negative 1, 3, times t. And we'll say t goes from 0 to 1. Because we want to be a line segment, so we say once you get to the end, 0 or 1, you stop. You don't keep going past there. Well, this is not really a vector function. This is written as 2 separate vector pieces. So let's distribute. So we get 1 minus t, 3 minus 3t, and negative 2 plus 2t, plus 2t minus t, 3t. Gives us 1 minus t plus 2t, that's 1 plus t, 3 minus 4t, and 5t minus 2. Or whichever way you want to write it. You write it as negative 2 plus 5t, where t is between 0 and 1. So that's the vector function. If I ask you what is the f, f is t plus 1, or 1 plus t. G is negative 4t plus 3. And z is 5t minus 2. But, again, specify the domain. If I ask for a line segment, you don't specify a domain, I have to take off points, because without specifying it, I would assume t is all real numbers, and that gets you a full line, which is not what I'm asking for. Alright, next up. Okay, now this next one talks about intersection, and that's a little tricky here. Find a vector function that represents the curve of intersection of a cylinder and a plane. So what does that look like in visual terms? Well, we get a cylinder, which would be, let's see, like this. X squared plus y squared is 1. And we get the plane, y plus z equals 2. So let's see. Y plus z equals 2. So that means, let's see, here's z, here's x, and y. or z equals 2 minus y. So, let's see. Okay, so if y is 0, z equals 2. So that's this point here. If y is 2, z equals 0. So that's out here somewhere. So we get this plane, which kind of goes like this, and it cuts through a cylinder. And so we get some sort of sideways shape. What shape will it be? Well, here's what we are going to do. I see x squared plus y squared equals 1. So this is going to be the most common thing we do when you see a circle. You will want to parameterize, or is it parameterize? I can never remember. Whichever. Circle x squared plus y squared equals 1. Parameterize means you want to come up with a parameter, t, where you can write both x and y in terms of t. So instead of having two variables, you just have one. So the common way to do this is to say x is cosine, y is sine. And then you say t goes from 0 to 2 pi, because that's a full circle. So that is 2/3 our vector function. What we don't have is z, but let's look back at this guy. Z is 2 minus y. So z, we plug in y equals sine t, 2 minus sine of t. So that's our function. R of t is cosine t, sine t, 2 minus sine t. Let's bring up a graph for this. I think that will be helpful. So let's go to our graphing software. And there are others like GeoGebra, but I am sharing the one that I was shown to me at the last conference, and I really like it. 3D graphing. So, this is a vector. This is a space curve. There we go. Space curve. R of t is what we said. And it's cosine of t, sine of t. And here's the earlier one we saw. Gives the spiral going upward. It's a little hard to see, but if we made it like 0.1 t, 0.1 t, you can see it a little better because it's smaller. That was the earlier example. But let's look at the example one right now. So z is 2 minus sine t. Now we get this sort of circle out in space like that. Does that work? Is that true? Well, let's do the other thing. What were the other pieces we had? We had a x squared plus y squared equals 1. That would be an implicit surface. We just state an equation, and it gives us x squared plus y squared equals 1. That's that cylinder. You can see it is in the cylinder, in fact. Let's make z a little bigger. Let's have z go up to 4 so we can see the whole thing. So you can see that's that shape that we have. I don't want to call it a circle. I think it's more like an ellipse in space. And if we also have z equals 2 minus y, turn that on, and we can see the way the plane cuts through it, it creates that sideways circle. Or whatever the shape is. Yeah, I'm not really sure what this shape is in space. I'm not you'd have to do some algebra, maybe some completing the square or something to try to figure out exactly what this represents. But we got the idea. This describes all the points. From above, it looks like a circle. From the side, it looks slanted. It is what it is. Let's do another example. One that takes a little more work, but is a similar idea. So, next problem was, find parametric equations for a curved intersection of the paraboloid 4y equals x squared plus z squared and the plane y equals x. This is a typo. This should say 4x. I will fix that before I upload the notes. So in your notes, hopefully it says 4x. So 4x equals x squared plus z squared. And y equals x. So when I see this x squared and this 4x in the same equation, my mind jumps to completing the square. So let's do that. 0 equals x squared minus 4x plus z squared. So I sometimes, I like to draw my little shapes here. Here's x squared, sides are x and x. Again, this part is unnecessary if you're good with completing the square and you know the formula, but negative 4x splits into negative 2x, negative 2x. So it's x minus 2, x, and minus 2. So you say, what is the area of this missing box? What's negative 2 times negative 2 is 4. So I add 4 here, and I add 4 here. So then I get 4 equals, this factors into x minus 2 squared plus z squared. Now this shape is weird. It looks kind of like a circle, but it's off a little. Maybe you know what this is, maybe you don't. I'm going to write a step here, which is strictly, you don't have to write the step out if you don't want to, but I'm going to explain it. Let's do a substitution. U is x minus 2. This becomes 4 equals u squared plus z squared. Well, this is a circle. And if we want to parameterize it, we would say u is cosine t and z is sine t. I know earlier I said x is u, or x is cosine and y is sine, but there's nothing sacred about x and y. Whenever you have it like this, of like something squared plus something else squared equals a constant, that's a circle in some sense. Now we need to sub back in. So we say u equals cosine of t, but u is also x minus 2. So x minus 2 is cosine of t, and x is cosine of t plus 2. I said y equals x, so y is also cosine of t plus 2. So cos t plus 2, cos t plus 2, sine t. Now let's go to the graph. And let's see how it's... Okay, so let's see. Our first equation, implicit. Again, implicit means it's not stated as like z equals 2x plus y or something. It's an equation. So let's delete these. 4y equals x to the second plus z to the second. Oh, that's not, it's a paraboloid, isn't it? Well, actually, I don't even know what shape that is. Oh, shoot. I copied it wrong. This is supposed to be 4x. There. That's a cylinder here. That makes more sense. Okay, the second one was y equals x. So let's do another surface. Up here, y equals x. So we see it cuts through. Let's make x a little bigger so that we can fit the whole thing. Alright, so now we can see the whole intersection. That needs to, y needs to get bigger too, doesn't it? Let's make the y also go up to 4. All right, so now we can see the whole intersection is another sideways circle. If we look down on it, what would this circle be? Let's turn off the cylinder. Or no, turn on the cylinder, turn off the plane. We can see what's the center is at 2. So it's a circle centered at 2, with this slanted plane cutting through it. So if it wasn't clear, this equation by itself, this x minus 2 squared plus z squared is 4. That is a circle in x and z, but it's centered at 2 with a radius of 2. The x minus 2 shifts it 2 to the right. And then the y is the same as the x, which causes this sort of slant in space where part of it is raised up above the other. And the last thing on these notes was you have a really ugly curve here. There is no way you'd be able to sketch this by hand, but we can do it with computers. Let's see what it looks like. Okay. So, get rid of that. Now this is given x is something, y is something, z is something I want to sketch. So we will use a parametric surface here. Because hang on a second. Each one is given in terms of oh, no, sorry. It's not a surface. It's a curve. So, parametric surface would be if we had 2 inputs. We're not there yet. So, it is space curve again. That's what I meant to say. So, x is... It's not... Turn that off. Best to not turn it on until you're ready to graph. Let's see. 4 plus sine of 20t cosine t. Y is 4 plus sine of 20t sine t. And z is cosine of 20t. It's kind of like a sphere, but I don't know what it's going to be. Oh, wow. What the heck is that? It's like a slinky. We said t goes from 0 to pi. So all our functions are trigonometric. So once you go from 0 to pi, you've covered everything. So that's what we get. This is the sort of thing that computers are great for. This is way too complicated for anyone to do by hand. So that's why it's good that we have this technology. All right. So that's that. I will see you on Monday.